from speech signals. So what I've shown here is a time domain waveform for the utterance ice cream for ice cream. Speech recognition is typically not implemented in cognitive architectures, or if it is implemented, it is implemented as a separate module. And why is speech recognition important and a difficult problem? So if you look at the spectrum for ice cream up here and the words ice cream, you will see that they look very similar. In fact, they are identical. And this is a loose demonstration to kind of show our belief that speech recognition is a much richer problem than just being able to list the sequence of sounds from speech signals. In fact, we believe that speech recognition involves a fair bit of language component, that is modeling syntax and grammar, and also modeling cognition, that is modeling the speaker's intentions, their goals, their state of mind, your state of mind, and things like that. So this guides us in our long-term goal towards integrating speech with language and cognition, and we believe that you could leverage mechanisms across these three faculties to aid in each other's tasks. The work that I'm going to talk about today would be isolated word recognition, which is a simple form of speech recognition. And already we can see the architecture is able to contribute a lot, and we're able to leverage a lot of mechanisms in the architecture for things like parameter learning, generation of the graph, structure reuse, etc. And Sigma's decision cycle will also be contributing towards selecting the most likely word. So as Paul mentioned, Sigma is being developed with three key goals or desiderata, and speech is an important demonstration of the grand unification goal, where speech, which is a subcognitive task, is implemented in a cognitive architecture, and functional elegance, where the same set of mechanisms that underlie other cognitive faculties is able to do speech recognition in a uniform and non-modular fashion. Thus, we believe that Sigma's key strengths of grand unification and functional elegance play a key role in being enabled to give us the fusion of speech, language, and cognition that we are looking for. So Sigma is constructed in layers, and where does speech recognition fit into these layers? So we have been able to add speech recognition as knowledge on top of the architecture without having to change anything in the architecture, and we believe this is really cool. So let's look at actually what we have to do to get speech recognition. Let's deconstruct speech recognition throughout the layers. At the cognitive architecture layer, you have predicates and conditionals, which are, you can think of them loosely as short-term memory and long-term memory, where predicates give you storage for things like perception and state, and conditionals bind the predicates via functions, and you can think of conditionals as long-term memory rules that act on the predicates. The cognitive cycle that is shown here, Sigma's cognitive cycle, is able to do the selection at the end of the utterance and give you the most likely word. Below the cognitive architecture layer sits the graphical layer, and at the graphical layer we use spectrographs. So the gradient descent learning algorithm in Sigma operates at the graphical architecture layer, and we shall see that it is able to learn all the parameters that are required for speech recognition. So how is a typical speech recognition system organized? At the input you have an utterance. In this case, I've shown the time domain waveform for ice cream, and you segment this utterance into roughly tens of milliseconds, which corresponds to the rate of change, and you get features that you can use in your main decoder. So this is the speech decoder, and the speech decoder does two things. It is able to translate the input features into sequences of sounds, and then translate those sequences of sounds into sequences of words or utterances. And this is typically done with the help of a language module. This is a form of a n-gram or trigram based language module, where your task vocabulary is organized as conditional distributions, where we say probability of next word given a context of words. What we would ideally like to see is a much richer language module, where you can do things like word sense, for example, and bidirectional flow of information, so that speech is also informing language and language is constraining speech recognition in some way. And we all agree that cognition influences language to a great deal. what is the interplay between cognition and speech decoding. And we would like to explore this fusion of speech, language, and cognition. So in this present work, the input features that we have used here are k-means clustering obtained from the speech toolkit hidden by HTK, but our approach is actually not limited by that, and we can use other forms of input features as well. So the dominant paradigm in speech recognition has been hidden Markov models, and let's construct a hidden Markov model for the word one. So you can think of the word one loosely as having three sounds, wa, and na, that are organized in a chain. So you get a transition function. And this transition function is essentially modeling variable length of the word one. You can say one or one. You can think of each sound as having generated a portion of the spectra, which is shown below. This is a frequency domain representation of the time domain waveform. And you can think of the sounds as having partitioned the spectrum. And each sound is responsible for generating a certain portion of the spectra. So we cannot observe the sounds directly. What we observe is what we get at our input. And thus we model a conditional distribution over the sound and the spectrum. And that is the observation function. So these are the parameters that we learn, or we need to learn to do speech or isolated word recognition. So if I were to just do a quick isolated word recognition, this is what a system would look like, where you pass utterances through each of the HMMs that represent each word in your task vocabulary, and at the end of the utterance you select the most likely word from there. I haven't shown the perception functions here, but they are there. So let's deconstruct speech at various layers in the Sigma architecture, starting with the graphical architecture. This is the HMM for the word one. I've shown 3 time slices where the state S1 generates observation O1 and moves to state S2, which generates O2, and finally moves to S3 and generates O3. This is the corresponding factor graph for the HMM. And we shall see how the factor graph actually generalizes the HMM. The transition function that governs the transitions between states is shown as the factor node up here, P. And the observation function of the HMM that is responsible for generating the spectra is shown in the P factor node. So factor nodes are representing functions between variables, and the variable nodes are the state S, or S1, S2, S3, and the observations O1, O2, and O3. So if we were to have a bunch of these HMMs, then you would need to just slightly modify the graph and use indexing. So what we have shown here is the state S1 for each word W. And so the important thing